Okay. So I'll go with this.
Okay.
Okay. Thank you very much to the organizer of this event, also for help right now. I will give an overview of NRGR, which is an acronym of Non-Relativistic General Relativity, funny name, which I will explain later. This is one of several nowadays field theoretical based tools available on the market to study compound binary dynamics. I've summarized the result of 20 plus years of work done by not only by me for sure, but a lot of people. And I will also touch upon works done also by other people in other contexts. There are so many that I literally cannot fit in the page, and it would just eat on my wall time just to quote everybody. So I acknowledge them here collectively, and if you want more references, we will discuss that. I'm happy to provide them after the talk. So since I'm the first speaker, give a little bit of context about phenomenology and also about theory. That will be absolutely not complete. So I rely on the other speakers to chip in and do their part as well. So, well, we live definitely in the gravitational wave era. We have 200 plus detections done by the Elbeke collaboration of binary coalescences up to, at the moment, the end of observation around 04, which is ending in the next few days. And many more to come with the planned future experiments, for instance, LISA, ET, and the Cosmic Explorer, which are supposed to be taking data in the 30s. And since we are basically in 26, you see times run, and these things will come soon. So we'll have plenty of observation with unprecedented sensitivities. That's clearly a huge motivation to study this system, in particular the binary system, which is the main source so far, and to do precision waveform modeling about this. Fair enough. To me, and if to a theoretical oriented mind, this is very more than that. And because the system itself is a beautiful physical system, the compact binaries are very simple in structure. They can be considered basically point-like up to very great precision. And yet, this simplicity married with the complications of general relativity can allow you, bring you to do very high perturbative calculations in whatever perturbative scheme you choose. There are many, and discover a very rich structure and discover theoretical problems, and etc. So there is an intrinsic interest in this system, which goes beyond the already wonderful phenomenology, which is present and waiting for us in the future. Just give you a few examples from my own garden, it is a post-Newtonian expansion. Just a list of problems which every step, every new perturbative step had to face, and some were expected, some were not. So it was really interesting and challenging every time. We start from 50 more years ago. Just the fact that GR is nonlinear, so it can source itself, so you have to invert some operators in the whole space for the standard sources. That was already, I mean, you don't think about it, but it was a problem. Nobody has ever done before. And then at 3pn, you start meeting the first divergences, and which are actually unphysical. They can, I mean, gauge the way in some sense. But at 4pn, they show up again, and this time they are physical because they are combined by logarithm, which are a testimony of a running of a quadruple coupling and of other couplings of a theory. And more than that, at 4pn, you start really to, things start become really technically difficult. In my approach, that is based on Feynman diagrams, you start to meet really complicated diagrams, and that was the first time we had to think, we thought about, I mean, particle physicists are very good at this, so we must ask them for help. They must be interested in this problem. And so that's where part of the story began. And then so on, okay, now we are at 5pn, we had other issues. We had this memory term which was elusive for pretty much some time, and now it is apparently being solved. And okay, so just to tell you, it's really a theoretical challenge and source of amusement every time you do something, you go to the next level. And this is the reason why, I mean, all these reasons combined, the phenomenology and the theory, are the reason why I like to show this Middle-earth map to show what happened to the field since 20 plus years ago, when I personally started to do this. There was the post-Newtonian approach, classical, done by Blanchet, Damour, with the Lagrange, with the Hamiltonian. There was on the other side some numerical breakthrough with Pistorius, etc., and to model especially the merge, and the EOB, which is effectively one-body method of Damour and Bonanno. I promised myself not to quote anybody, and continually doing it, but okay, never mind. They deserve it, which is a resummation, a clever way to resum and to make the two regime talk, so the inspiral and the merger, and to connect them in a whole meaningful waveform. And sometime later, the landscape has changed. There are a revival or new approximation schemes, perturbative scheme. The post-Newtonian was already there at the beginning to study the multiples emission. Now it has been revived with the advent of amplitude approach and Waterland approach and the new link between the bounded number problem. And there was also a revival of a surf force, which is an expansion in mass ratio. So there you don't expand around Minkowski, but around Schwarzschild, and we'll have to talk about that later on. It's a colloquial, right? Yes, so okay. So I don't have to spend time on that. People will, you will hear much more informed speakers about that. And in all of them, there are some EFTs methods, filtering methods, borrowed from basically from particle physics, because they're being developed historically there, but they apply perfectly also to this problem. So yeah, okay, that's, I think, enough. Oh no, I mean, I can just illustrate, since I really am the first speaker, how these approximation schemes are related to one to another. The post-Minkowskian is an expansion in G Newton, and the post-Newtonian adds the information that the system is bound, so the Vega theorem, so this V is related to G, so you expand also in velocity, and the post-Newtonian is what you need to do if you want to meet phenomenology, because this is what matters, okay? Every vertical line here is one step more towards phenomenologically relevant, complete waveforms. And we are at 5 p.m. right now. On the other hand, the post-Minkowskian aims to a much more difficult task. So it doesn't do the expansion in velocity. It takes all the velocity, arbitrary height. So it is good also to study scattering problem. And it's in the spirit what I was saying before. Phenomenologically, it might appear less interesting because, for instance, the state-of-the-art G4, G5 nowadays is covered just the 3 p.m. complete level for the phenomenology. But on the other hand, you have a lot more information, which is very useful, both theoretically and also to check and to overlap with the post-Newtonian theory when the overlap is possible. And the same for the mass ratio expansion. For instance, here I'm showing if you express the energy of a binary in terms of this gauge invariant frequency revolution, which is scaled as the velocity, so it's a post-Newtonian parameter, you see that at every post-Newtonian degree expansion of energy, you add one power to the polynomial expansion, includes one more power to the polynomial expansion of a mass ratio, which is a very simple algebraic property, nothing mysterious in that, but again, it's telling you that the people who work in cell force, they have access, they completely go down here in this, say, one order new, and they go down and can uncover post-Newtonian levels, which we do not have access completely in the post-Newtonian approach. Okay, so the different expansion schemes, they talk to each other and they cross-inform each other in a very productive way. So let's now I start to describe really what my business is about. We basically take this binary system and two-body system in general, and we integrate out the gravitational field, which is exchanged between the two bodies. So basically, I write down in this fancy way, in the path integral, you have a fundamental action, which is general relativity plus a gauge fixing term. Then you have a coupling to the particle. And you basically kind of integrate out the exchange degree of freedom, and we are left only with an action for the positions of the particles and the field at infinity, that is the gravitational wave which we observe. While the field we integrate on is the thing we do not observe, which is the local exchange, gravitational exchange between the objects. Why I am formulating in this fancy way when, after all, everything I'm doing here is solve a classical problem. I'm solving the equation of motion, okay? This is something that also Blanchet was doing in another way, but similarly. So just to say in a few words, I don't have loops here, okay? It's all a classical problem because the loop scales like the ratio of h to the angular momentum of the sources, so it's completely suppressed. This is completely, I mean, what can be more classical than two neutron stars, okay? So classical problem, but we borrow the language and techniques from quantum field theory because it's organized and it allows you to be more efficient. For instance, if you just think about the point-like singularity, which is a classical problem, okay? If you just formulate in the language of quantum field theory and you work in the Nimbreg, they just give you to zero vanishing diagrams. So you get rid automatically and you can regularize already a lot of classical divergence. And then, okay, you go on, you exploit this technology and you start building your perturbative expansion in the form of diagrams using the big contractions. And we basically have two products which we are interested in. The first is diagrams. So a bit of terminology. The black lines are the particles, the black holes. They are completely external sources. They don't have dynamics in this approach. They are given, okay? The orange thing is the gravitational degrees of freedom which are exchanged between the particles. And eventually the green line is the waveform, the gravitational field which we measure at infinity. So we are interested in two products. One is gravitational wave emission. So whatever complicated way this system has to emit gravitational waves, and what we can measure in observatories. And the other is diagrams where there is no emission, and by this means you can describe the dynamics. The final product of these diagrams is a Lagrangian or an energy, so a functional which gives you the classical equation of motion for the system. Okay? So this weak expansion, contraction, corresponds to an expansion in G, because every coupling here is a square root of G dimensionally as a strength. And so we are in the regime so far of a post-Minkowskian expansion. What does this particular version of effective field theory, which is an RGR, okay, the name comes from NRQCD, non-relativistic QCD, because it was first applied to some regime of wavy quarks, non-relativistics, and the same machinery can be applied to gravity. That's the name, non-relativistic general relativity. And in this case, we just, on top of it, we add the information that we had in a closed system, and so we use a Villiard theorem, and we add the expansion on top of it. So, I mean, pictorially, this just amount to say that we have a scale separation due to the fact that the system is non-relativistic. So the wavelength of the wave is much larger than the size of the system. So on the one hand, the coupling can be described in terms of multiples, something we already know since, I mean, Thorne and even before. And on the other hand, technically, and this is important, when I have the propagators of the exchange fields between particles, we can trade them since the frequency is much smaller than the inverse separation of the actual separation of the stars. we can trade them, so the wave number of exchange graviton, we can trade this propagator by this resummation, okay? And that makes our life more simple because the integrals are simpler, and that's the reason why we can go that far in the post-Newtonian expansion, contrary to our post-Minkowski colleague who had the hard work and they keep this in the full form. This doesn't come without consequences, and I will touch upon that in a while, but let me first continue the overview. Yeah, so the difference, as I was saying the post-Minkowski version of this approach is just not to expand anything, compute the integrals as they are. Of course, it's much more difficult. You have to use fancy techniques, but once you have that, the result, you stay lower in PN, but you get more information on what on the diagrams you can do. Another approach is the so-called worldline EFT, I like to mention, where the sources are not frozen, they become dynamical. So you write the composite position of a star in a classical position plus a fluctuation, which also becomes a variable in your path integral. So you integrate also over it, and then it becomes directly observable. And for instance, you can use it in scattering problem to give you directly the scattering angle, because you just can observe the momentum before when the star enters the interaction and the momentum when the star exits the interaction, and you just write away the answer. While in our approach, it's a little bit more indirect. You have to first derive the Lagrangian, then the equation of motion, and then you prepare the system, and you compute the deflection, and then you have a scattering angle, while this method is a way to have it right away. So you see, even within these kind of methods, and not even touching on amplitudes, there are several versions, several flavors which can be applied to several different physical problems. And then there will be amplitudes. I don't have time to touch upon that. I hope other speakers will, I'm sure other speakers will be more exhaustive about that, but of course, in this case, the problem is completely different. You just study the quantum scattering of some gravitational degree of freedom, and you have to take the classical limit, and you can also derive match to an FT field theory, derive a potential which will give you that scattering. But in this case, the main thing is that you work directly with gauge invariant quantities, like particle physicists start to do for the whole, the whole history of physics, right? They do scattering, which is a clean process, and then you work back in the information. Okay, but I will not touch about that. I'm sure the speaker will do. So let me go back to our business, and let me start. Wait, I can skip. I told you there are two products of this approach. One is the binary dynamics, the energy, and one is the gravitational radiation. Let me start with the binary dynamics, because I would say it is more fundamental in some sense, because even if you derive the gravitational radiation emission in terms of quadrupole, octupole, etc., when you have to understand, to know how this quadrupole behaves in time. And so this information is primordial. Prior to do anything, you have to understand the dynamics at a given post-Newtonian order. Also, binary dynamics alone can provide information which can be used by the effective body. So it's already informative on its own. And yeah, this is it. And there is also a further simplification which occurs in the circular orbit, which is more or less the coalescence which have been observed so far. You can just shortcut the calculation just by imposing energy balance. So you know the power on one side, the energy on the other side, and you can compute the phase of a gravitational wave with high precision, more precise than what you can do with amplitude. But if you are a phenomenologist, you are more interested in the phase because this is a critical parameter in the match filtering in the template bank. So you can allow yourself to miss a little bit of the amplitude, but if you miss a phase, you're screwed. So that is more importantly observable. But of course, this simplification is spoiled once it's introduced in centricity and spin precession. So that's another problem. But now let's focus on binary dynamics. I will describe briefly how this is done. Yeah, so it's really simple. You just have to know the rules and just do the calculation. If you want to compute the Newton potential, you have your two stars, and the lowest order in G Newton and in the velocity, you can exchange basically 0, 0 degree of freedom. You have your coupling dictated by the Lagrangian. You have a propagator. And as I said, a first order in the expansion, you just neglect the time derivative with respect to the wavelength. And you have this. And then what you have to do to the potential, you compute the diagram, which is basically taking the Fourier transform, and you get the one over the potential, okay? You want to do 1pn. Again, you just expand these vertices and propagator one velocity more, and you introduce new diagrams, which have one power more in velocity or in the G Newton. In velocity, power more in velocity, same diagram, you have exchange of a 0i component. And if you want one more power in G Newton, you have two exchange of particles. And you go on. And it takes really, if you have the right tools, you can give it as an exercise in 1 hour, you can compute the Einstein-Fermat Lagrange. Okay? Yes? Physical interpretation of this last one. This last one? Yeah. Oh, one black hole emits two, not graviton, 2 degrees of freedom. It's a double vertex, okay? And they are just to exchange with the other particle. It's just not. Okay, so we just have to move on. More complicated diagrams. At 2pn, you have another kind of, you just add more complications. This is one, you exchange an Ij degree of freedom, and then that the non-linearity of gravity comes in. You have a triple vertex. It can split in two, 0, 0 degrees of freedom, and they are both absorbed by the other particles. No problem. You just have to compute. You put inside the particle vertices. You put inside the bulk vertex dictated by the Ricci term in the Einstein-Lagrangian, which you can express in terms of this A00 Hij. You have a propagators. This time you have a double integral, and you can do with standard formulae again with not so much hassle. And a G cube star, yes. Because yes. You already said that some loop diagrams you do not keep because it's quantum mechanics. How do you know which one to keep, which one? This is not a loop. Good question. Thank you for asking that. This is not a loop because the black thing is a classical field, external source. Okay. Another way to draw it is just collapse this to a point. It's not even a good way to see it, but this is not a loop. Okay. A loop is a loop involving only gravitational degrees of freedom. Okay. They look like loops formally for the particle physicists. You look at the denominator, you say, oh, this is a loop. But physically, this is not a loop. Okay? So keep that throw away, or keep the ones with one of them is the word. You just don't look at the black lines, and this is you see there are all three diagrams now. Okay? This is the rule. And I didn't make up a rule. They come from the formalism. Just to, of course. Okay, so G cube, more complicated. This is a two-loop integral. We can still do it. Okay, and once you're able to do this diagram, you can do 2pn, the complete 2pn Lagrangian, which is kind of 15 diagrams overall. And you can assign as an exercise to, as master student. It can be done in really quick time. But of course, I know this is a perturbative expansion. At some point, you get in trouble. Okay, G4, G to the 5 diagram. You start to have hundreds of diagrams. You start to have 3, 4 loops equivalent diagrams. It's become very complicated. That's when we started to think, okay, we cannot do this alone. We need help. And for instance, I remember we contacted Pierpaolo Mastrolia in Padova, and we told him, do we know to do this? Oh, yeah, sure, it's easy. Oh, okay, good. Help us. And, other people did the same part in the meantime and afterwards. and expanded this on top of what we are doing. And okay, so more complicated, more diagrams, but still we can rely on the experience of particle physicists to match pretty much of them and of the technology. So we learned about all these Laporte algorithms, things which I didn't know before, and I had to at least learn what they were. So with this, we can do 4PN, modulo some complication, which I already mentioned before about the infrared divergences, which I will touch upon now. A 5PN is pretty much the same, just you have thousands of diagrams, but with a good code, for instance, Bloom, Leimer collaborators, they build a code to do this, and it's systematic. Once you have a good code and a good computing power, you can do this. And again, there is a part which is being verified with the Minkowskian colleagues up to G2/4, and these diagrams, which are really post-Newtonian, too difficult for the moment with one to a post-Minkowskian, but they are kind of, for the kind of lucky factor, they are easy to do in this order because they are factorizable, so they can break down in easier diagrams. But I mean, it's a technical detail. But we have all the potential modes of the 5PN. When I mean say potential, I mean all the diagrams in which the propagators have been replaced by an instantaneous propagator. Okay, with the thing which I was mentioning before. This is not the end of the story, because already 4PN, I cheated a little bit before, you start getting into trouble because exactly of this approximation. If you trade this propagator for this one, you can see by yourself that the higher behavior is bad at some point. And it blows up in your face. In these diagrams, they have infrared divergences. That is telling us, yeah, you're missing something. What is missing is that is the pole contribution for this diagram. This pole contribution is the fact that the two stars can start not changing only potential modes, but gravitational radiation, which is emitted by the system, backscattered by the curvature, for instance, like here, and then reabsorbed by the system. This cannot be seen by this approximation, but can be seen by another approximation, which is the multiple approximation. You can build the Lagrangian in terms of multiples, compute the diagram, and what you find is that these two contributions, which are very good in their appropriate dynamical regime, and are very bad in the other regime, because this is IR divergent, but this is UV divergent, because when you treat the two objects like the point like source with multiples, when you shrink the size of the source to 0, you get UV divergences. But if you do things appropriately, for instance, if you use a good regulator like DIMREG, you see that the two dipoles cancel each other, meaning that, okay, you were not doing it wrong from the beginning, but it's a mathematical fact that these two long integrals, if you sum them together, you get the right contribution plus stuff which is vanishing in DIMREG. So you cancel the poles, and you're left with some finite part, which is the prediction of the theory, and the logs, which are a testimony of the running of a quadrupole with the scale where you're observing it. Yes, these are UV divergent and these are IR divergent. Yes. Everything I do. You can do it, but it's easier to do it in DIMREG. But you can do it. I mean, you can use the regulator you want. You know, the brutal cutoff spoils you some symmetries. I mean, it's just more handy to have a DIMREG. But yes. Sorry? Yeah. No, it's not an exclusive. Absolutely, you can. I mean, you have UV and IR divergences also in the other diagrams, but this is the first time, the first instance where we meet them. For sure, it's a general phenomenon. And the post-Minkowskian colleague, when they do these diagrams, they don't expand the propagator. They find a difficult integral, but it's perfectly finite, and they don't need to do this. because it's all inside there, okay? But of course, you don't have to think that all this is just an artifact of our approximation, because we are left with some physical information, which are the logs, okay? We found these logs in this way, but they are there no matter what, or even in the Minkowski approximation, okay? Because they are the running of a quadrupole coupling. Okay, so this is for Pn. Now, okay, we understand that we have these states to take into account. We can compute all of them. You can, the 4Pn when you happen when you have a quadrupole here. When you have other multiples, you have 5Pn effects. And you can also replace the field source by the mass of the system, also by the field source, by the angular momentum of the system. And you're gone, okay? You have all these family of diagrams. You just put a multiple you want, and you have some tails, which are corresponding logs, which each of them cancel the corresponding divergence in the theory, except for this one, which is finite for an accident. And you can move on and deal with everything. And we arrive at 5Pn. At 5Pn, there is more stuff than that. So far we studied the potential mode, we studied the tails. In 5Pn, you still have to incorporate the dynamics, the memory, which is basically, yeah, forget this one, it's a bit technical, but this is, the tail is radiation emitted but scattered and reabsorbed. This is two gravitational waves emitted and colliding and producing another gravitational wave which is absorbed. Okay, it's a qualitatively different process because also this now is a on-shell propagator and becomes more complicated. And to this you had to add the radiation squared. You know the radiation is a V to the 5 effect. So it's a 2.5Pn effect if you do the counting this way. And if you square in the sense, which I'll explain you afterward, but it's easy to guess, you get a 5Pn effect, which affects your 5Pn dynamics. The new thing of this effect with respect to this is that they are a mixture of conservative and dissipative stuff. The potential mode are all conservative. You don't have poles in the propagator, it's just instantaneous stuff, conservative. The tails have a dissipative part, but it can be handled in an easy way. You don't have to worry about that. It's also non-local, so it's very easy to single out from the conservative part. Here it's all mixed together. There's no way to disentangle them, so you have to use a formalism which is appropriate. And the formalism is the in formalism using Kelvin variable. I don't know if you're familiar with that, but it's standard procedure. Again, one of the many tools that this beautiful language, which is a field theory, give us. That is, you have to double the degrees of freedom. You have to allow two time paths, one going up, one coming down. And then you have to build smart variables. And once you've done everything, you have a final product, which is an action depending on the plus and minus variables. And you have the equation of motion deriving with respect to the minus variables, and then taking the physical limit where x1 is equal to x2. So x minus becomes 0 and x plus becomes your variable. It seems a bit complicated, but this is what you have to do in every instance, even in classical physics, when you want to represent in a Lagrangian way some dissipative process, okay? Of course, if your final product comes in this form, which is the same form where you started about, then you have a conservative Lagrangian, and you can forget about Kelly's variables. But with these new phenomena, memory and radiation emission squared, you have dissipation, and that's a way to do. It's not more complicated. You just add a little bit more variables to the problem, but the procedure is still simple. So for instance, if you want to study emission in the first, the emission contribution to energy in the first instance, you have to double with degrees of freedom. So the only allowed diagram for the rules of the Kelly formalism is the one where the Q plus emits a graviton with a retarded propagator. Now the propagators have a sense. We are using the retarded propagators and absorbed by Q minus. You have your diagram and you can evaluate. If you don't do that and you forget about this diagram is 0. You don't see the dissipation. But if you use the Kelly's variable, you have a Barton acceleration, dissipative term. And of course, if you just plug in this Q5, the Newtonian acceleration, you have a Barton term, 2.5 pn. If you plug in the Barton term again inside, iteratively, you start to generate a 5 pn contribution to the dynamics. And then there is the memory. There are the diagrams which I showed you before. You have to give there are rules to give the appropriate propagation direction to the retarded propagators and to distribute the Q plus and minus variables. Yes?
Maybe it's obvious.
Yeah.
Why is, you call it memory, in a sense, why I should see that there's the memory?
I call memory anything which involves in the waveform, this is when you have two, imagine the waveform, the open diagram of that. Two graviton waves emitted, they collide, they make another one. That gravitational wave will carry information, of course, inside the light cone, right? And that's why traditionally this is called the memory. And now we get, used to use the term memory. For me, memory is anything which involves 3 quadruples. But you're right, these names, they start from the phenomenology, and then they are carried in. So yeah, there might be, also there is a linear memory, the nonlinear memory, and the DC memory. They are related to this effect, but each of them seen from some angle, okay? And I'm taking this angle here just because in the post-Newtonian expansion, the 3 quadruples term is what next FIPN, but it's the right observation. Yes, sometimes, when you bring people from different fields, they use terminology, and it's good to stop me and point this out. Okay, again, this calculation was bothering us for a while. We seem not to be able to get it right, but finally, Rafael Porto and his collaborators managed to get this right, and this is the final brick of the 5PN dynamics, which gives a scattering angle, which is compatible with the calculation which was already done in theory. And so now we can really say that the 5PN calculation is consistent with every other observable, and it's, I would say, almost complete. Yes? Because the equation of motion is this, so you need precisely 1 minus. The rest doesn't give you, it's a formalism. So you just want one minus in every diagram. That's the reason. There is spin as well. I didn't mention it, but if you want to include spin in the formalism, you can do. It's just one more operator on the word line. You have to be careful. It's difficult. It's very gauge redundancy, but it can be done. Again, explosion of diagrams at some point, but it can be done. And there is the state-of-the-art is summarized in this nice table made by Justin Bynes some time ago. I think it's still accurate. So you see, 0 spin, this is what you've done. You can include 5PN. If you have 1 spin, you start from a spin orbit interaction at 1.5 pn, formally. But actually, for real neutron stars, it is much higher because they don't spin so much, and etc. So this is the picture in this moment. And I want to emphasize that all the state-of-the-art results in post-Newtonian physics, with and without spin, are being reached with NRGR. Not exclusively. There are other methods which had obtained covered some of these sectors, and in some cases before us. But NRGR is the only approach who had made all of this, okay, which is a frontier in every sector of this theory. This is not true in the next other page, which I'm turning in, which will be shorter, because in that sector, NRGR is not the frontier, okay? In the radiation sector, so in the diagrams in which have some gravitational waves escaping at infinity, like instead of being trapped like here, the absorbed. Now, if you just study this sector, the state-of-the-art is provided by the classical approach delivered by Blanchet, which is a multipolar post-Minkowski approach, perfectly classical approach. You can argue that this is an FT on its own, because you just describe it, you acknowledge that seen from far away, the system is described by multiple degrees of freedom, instead of of the individual position of the particles. I'm going to summarize the result of the method in the language of NRGR, even if it was not obtained by NRGR, because so you have a consistent picture and drawings are nicer to visualize, okay? So first you have your Lagrangian, which describes the interaction of a system with the gravity at the large scale. For instance, this is the quadrupole coupling, which gives you this diagram, which is a quadrupole emission, which we all know. Now you have to tell me what is a quadrupole, because the quadrupole is mu xi xj at leading order, but then the mutual interaction of the particles give you a relativity correction. And this is what exactly what we do here in NRGR, or what the NPM people do in the other way. So they have to integrate in the internal degrees of freedom in diagrams where the graviton is emitted. They obtain a final product at a given Pn order. They identify the graviton emitted with this term just by looking at the symmetry transformation under rotation to select the quadrupole. And they say, okay, this result is the quadrupole. So you have a Pn corrections to the quadrupole, okay? And then there are other, of course, again, once you have this quadrupole coupling, you have to know how the quadrupole evolves, and that means that you still have to know from ab initio you must already have solved the problem for the binary dynamics at the given post-Newtonian order. Otherwise, you are just a formal expansion. You cannot not solve the problem until the end. And of course, this was just to give the correct post-Newtonian correction to this simple emission, because you had to put the Pn correction to the quadrupole, but then also all the multiples enter in more complicated diagrams, like the tail emission, the tail of tail, and very complicated diagrams like the tail of tail of tail, the tail of memory, okay, they involve a lot of stuff. They are very difficult to solve, but these smart people managed a couple of years ago to complete this emission, and that it's thanks to them that we now know the phase of a gravitational wave up to 4.5 Pn. So the templates which are used in LIGO, they use this result, which is pretty new, okay? We knew the things up to 4 Pn until some time ago, and now it's 4.5. Yes?
Is there a way to understand why your approach is very difficult?
I'm going to say, there's no reason, it's just hard work. I mean, especially with the NPM people, we talk a lot, we use the same gauge. It should be doable. It just, I mean, somebody has to do it, and somebody should do it. I'm advocating for that. But I'm, they are the monopolist of this business so far at this order, and it's not good. They are great people for sure, but so it will be interesting to do that. No obstacle in principle. Multipolar post-Minkowskian. Now, so just to tell you what we can do now, the last result which we have is the 2.5 wave with a memory term, okay? We get this last year, and it is perfectly matching the NPM result. This is the state of the art of NRGR so far, okay? But there's no reason for which it cannot be done more. Now I have 10 minutes, and I want to spend them still talking about radiation. Since we don't have anything relevant phenomenology to say here, I want to go and make an excursion on the very theoretical side. And I want to talk about the running, the beta function of the multipoles. And just to insist on the motivation, I'm quoting this paper of Steven Weinberg, who said he was already thinking about this problem, infrared gravitons, it's the same process. And he starts saying, it would be difficult to pretend that the gravitational infrared divergence problem is very urgent, phenomenologically meant. And he says, my reason for attacking this is because I can. Great, that's really good spirit. And then he goes on, of course. Second reason, something might go wrong. You have to be consistent, be sure that the theory is consistent. Third reason, because you can learn something. Sure, but okay, in this spirit, since we can, let's do this. So my idea is, the idea is to study this kind of correction to the tail and tail of tail emission. And if you do this, you discover that the first order is finite, of course. The first correction is IR divergent. The same divergence which Steven Weiber found, or knew, we didn't find it, it was already there, he explained it. And you go on, you find IR and UV divergences. So the IR divergence, as Weiber said, they turned out to sum up in a non-observable phase. Because every multiple you put in, the IR divergence does not depend on the multiple, and the infinite sum goes up into a phase. So if every amplitude of your theory, every single amplitude has the same phase, you cannot observe it, okay? There is no interference which I give you, they are all the same. And so we are left with a UV divergence controlled by this beta, which is a coefficient characteristic of every multiple. For the quadruple, the number is 214 under 105, and it is what it is, okay? I already called it a beta function because you know where I'm going. How do you cope with this UV divergence? There are basically two ways. One, you know the microscopic theory. This is what you do. We know that this system here, if you open it up, it's a binary. So you do the matching at the appropriate order, and you find that if you compute the quadruple at the appropriate order, you have leading orders and a correction which has an infrared divergence seen from the near zone theory. And as it happened before for the energy, the infrared divergence in the near zone, if you just plug it in the amplitude, cancels the UV divergence computed from the far zone diagrams. Okay, they cancel, and what is left is a logarithm of the ratio of the two scales of a problem, that is the wavelength, 1 over omega, and the orbital separation. And you see the dimensional parameter mu just goes away, okay? So this is one way, but this log, you know, the divergence cancel like we've seen before, and the log stay. Another approach, if you are from particle physics, is, okay, I don't know anything about the infrared, the microscopic theory. That system could be anything, and what do you do in quantum field theory when you have a UV pole? You just say, okay, this is a bad coupling, and actually, whatever it is inside my fundamental particle cues the divergence. So the real coupling is related to the bare coupling by a divergent relation. Oh, I forgot the epsilon UV, sorry. There's a divergence here, okay? And then when you express everything in terms of normalized coupling, everything is finite, but what you get is that your coupling transmute with dimension, okay? A different value just because depending on the scale where you do the matching. So we can compute the beta functions for the multiple, but the interesting thing is that since, for instance, the quadruple couples to the mass, for instance, in the tail diagram, then this log dependence, this dependence on the scale is transferred to the energy and to the Lagrangian. Pretty much like, you know, the vision of a charge of electron, which, you know, with virtual particles, the more you go deep in, the more the charge is the same thing, no? You can imagine that you have your binary system, you have two guys measuring the energy, and for the guy here, this tail emission by graviton emitted and scattered, if you are inside, you classify this object as radiation, you don't put them in the mass balance. If you are very far away, you don't even see them, and they are in the mass balance. And so that's basically a visual thing to describe the appearance of this transmutation, which generates logs in the energy function, and we can compute using the renormalization group scaling all the logs associated to the quadrupole. They are governed by the beta function, and they appear in this fashion. I remind you, x goes like v squared. It's a positorial parameter. It's basically the revolution frequency of the binaries. And we can, this is, goes up to infinite PM. You can find trace, and it is universal because here I didn't even know that this system was a binary. Okay, these logs, I mean, there are finite parts which are specific of a system you are dealing with, but the logs are universal as it happens in theory. Okay, and so this is universal. They must be easy to compute, and they are once you know what they are, and we can compute them to any PN order. But of course, now it's interesting to check it if reality, if we did it right. And of course, you see you go in looking at the system, and you look for the logarithmic terms in the energy function, and the first appears, as I mentioned, at 4pn due to this diagram, and the coefficient, you just do the math. It's exactly what was predicted here. But you can even go higher in PN. I mean, the state of the art is 5pn, and the next term here is 7pn. If you just look at it, but if you just are happy with partial results, the PN, the energy function, we know pieces of information at higher PNs. So this time we could do directly look for the log terms at 7pn, and we find this number, which also fits. And the self-force people are able to compute the energy function to the first order in perturbation against Schwarzschild up to 22pn. This is one self-force effect because one power more in one mass ratio, and you see in the energy function, when you have nothing, this is Schwarzschild. You sum this number, you have Schwarzschild. If you have nu, you have the first self-force. And looking at these people have been able to compute it up to 22pn. We did it before we came up with that, and so we went to check, and these are the numbers, and they fit to a spot, to the prediction. Okay, so that's funny enough. I think I will basically wrap up here. What's the outlook for the two sectors which I touched upon? Quantum dynamics. In principle, there are no new obstacles, I would say, up to 7pn. At 7pn, you have a tail of tail, which I don't even know what it looks like, okay? I mean, yes, I do a bit, but it has to be studied. So up to 6pn included, which is pretty much desired result if you want to do physics with AT, probably. You should boil down to compute more difficult integrals, which is maybe good news for waveform modeling, less good news for theorists. But yeah, I might be wrong. So I've been wrong in the past about that. So I thought 5pn was easy, and it was not. So don't take my word. But this is my expectation that doing 6pn is just more hard work. For the radiative sector, the multipolar problem constraint approach is, I asked them, so it's a very word, it's scalable. Now it's 4.5. Going 5 and 5.5 is not a big deal, just more multiples should be done. Energy calculation, yeah, somebody should really do that. If there's no reason, I'm too old for that, so don't look at me, but it's a very good project on several years. And of course, especially in this sector, but also in the other, amplitude methods can get in. They're getting more and more powerful. And I'm looking forward to hear about this in the workshop, and that can be also another big thing. And I think I'll finish here, and thank you for your attention.
Thank you, Stefano, for this very nice introduction. And now there is time for questions.
In the last part of the talk, where you compare against the self-force calculation, where you have to take this ratio of M2 over M1, in your expression, where is that ratio?
The ratio?
Yeah, the M2 and M1.
You mean this way?
Yeah.
What is the question again?
I just want to understand the notation. Where's the ratio of masses? Where does it come in?
Okay, you take different diagrams, like say this one. No, this one is not good, but okay, yes. This one is 3 powers, 3 vertices attached to particle 1, and 3 vertices attached to particle 2. So it is M1 cube, M2 cube diagram. And then you translate it into, you use the mass variable, the total mass and the symmetric mass ratio, which is new to the cube. So this is the most higher self-force diagram. Other diagrams like this one, this is one self-force, basically because it has only one vertex attached to one of the two particles. So in the limit where this is much heavier than the other, it is basically the only thing which survives in the Schwarzschild limit. All diagrams where you have one thing attached to something and the other. The first self-force limit is that when you have two, this is two self-force, and so on. That's the outcome. It's very simple algebra, nothing mysterious.
Okay, thanks for a nice talk. So for the last part of the energy renormalization, is that sufficient to get this beta function by knowing the quadrupole moment renormalization, or do you need more?
By using just a quadrupole, I can get the leading order of each new power of logarithm which appears. So I get the leading order of log, the leading term of log square. If you want the sun leading, you had to introduce the beta function of the orthopole, which by the way we know. And I forgot to mention, sorry, because this beta function, at first we did it wrong, and it can be done also by other methods, black hole scattering on the test mass, and also black hole absorption of gravitational waves, and like did Rodolfo Russo and Fucito and collaborators, and Para Martinez and collaborator. They did it, they found a different result, and so we went back and checked our result, and it was wrong. And now we agree. So there is plenty of methods to compute this beta function. Now we know that. So if you know the beta function of the orthopole, you can work this out and to the next order, and maybe cover a bit more space.
Thank you.
I also have a curiosity, like phenomenologically so far, which order was necessary to have a decent prediction, and how could it improve with ET or next one?
I mean, for the tension, the bare minimum is 3.5. Now, I mean, 4 was routinely used. I mean, 4.5 is pretty recent, and there were many observations where it was enough. Now, the PN series is asymptotically convergent. So you don't know, every time, we don't know what you are going to find. There's no way. I mean, it can blow up in your face at any moment. So I mean, if just by expectation, you would think that for ET, you want to go certainly 5 or 6. But, you know, there are, if you just, depending on observables also, some orders turned out to be more relevant than others. And there's no way to do it until you do it and you compute it. But generally speaking, 5 or 6 would be good. Certainly 4.5 for ET is not good, because this is so sensitive that once you have a big signal, which you'd get with SNR 1000, if you don't get it right, the residual are going to spoil all the other thousands of small signals that you can detect. So you must be precise, not for detection, but for parameter estimation and subtraction of the many signals you will have.
Also another small, yes, please.
So it's a very naive question from like a gravitational wave experimentalist, but at some point, the black holes, they have a finite scale, and you need numerical relativity, and they merge, and all PN orders won't help you there. But where do you see it in this formalism? Or you never see it, and these are just point particles?
I didn't touch upon a lot of things. First of all, I didn't touch upon finite size effect, which start to be, I mean, equational states of a neutron star or of a black hole, if it has any. And also this thing, I mean, this talk was centered about the inspiral part. The plunge, at some point, you know, the object become relativistic, and you cannot do that much, and then you go numerical. So the actual waveforms, they are made just by gluing together the information from the spiral part, which is analytical, and the information from the plunge, which is numerical. and harmonizing them, especially with ARB formalism. So at some point we had to stop.
Understood, but is there a marker there where plunge begins and where that
Sorry?
within this formalism, where do you see where that starts? Is there a
No, I mean, it's just the expansion parameter X, if you want, which at some point, if it is too big, I mean, formally, this is a Lagrangian for the two-body interaction.
Okay.
This Lagrangian is a good description of the system if the system is not moving too fast internally.
Okay.
You can add? Yes. Thank you.
To add to this, to what Stefano said, at some point the theory predicts its own demise in the sense that you will lose more energy than you put in. And clearly that is where you should stop way before that happens.
Yes, very good answer.
I had another quick curiosity. Eccentricity in this formalism, would it be like a breakdown of the static sources approximation? How do you account?
It just, I mean, there is no eccentricity here. I mean, the formalism is generic, but of course the application is more difficult. First, you cannot use your shortcut anymore. It becomes more complicated, and with precession, it's a complete nightmare. Second, if you have a very eccentric thing, velocity can be pretty high in the aphelion. And again, from the post-Newtonian point of view, it's very bad, but amplitude, if you do post-Minkowskian, then you can also try to cover the space more. That's where complication comes in. So far, we didn't need that, but for sure, especially in LISA, we will need to do that. For the moment, I mean, there is one event in LIGO, people were discussing whether it was an eccentric because the waveform was a bit strange, but all the others are perfectly circular because, you know, the radiation.
Yeah, thank you very much. I'm just curious, to what extent have perturbative methods like yours been generalized to scalar tensor theories or beyond GR?
There are some work. I don't know the details by heart in the moment, but I mean, I was advisor of a PhD thesis where this was done up to some extent for some scalar tensor theory. And I mean, it has been done. I do like to look it up, but people are doing this. I mean, just doing this phenomenologically to first perturbative order would be meaningful. So I mean, I think people are doing,
to the
but
point about observations that
yeah.
tested. Yeah.
Absolutely.
Okay, then if there are no other questions, let's thank Stefano.
Thanks a lot to you.